You think you know magnetism. Iron filings line up around a bar magnet. Opposite poles attract. Electricity flows through a wire and a compass needle twitches. Basic physics taught in every classroom. But one man in 1831 saw something nobody else could see. Not a phenomenon, a reality. Michael Faraday looked at empty space and knew it was full. He saw forces as physical things stretching through the void. His peers called him wrong. They said he lacked mathematics. They said he was a bookbinder playing at science. But this blacksmith's son, with no formal education beyond reading and writing, changed how we understand the universe. He proved that space itself could carry power, that magnetism was not action at a distance, but a tension filling the room, that the invisible was more real than the objects we touch. And he did it without a single equation. The way Faraday understood magnetism was not just genius. It was a complete reimagining of physical reality that scientists rejected for decades. Faraday later recalls being given one loaf of bread to last an entire week. No money for school beyond the basics. At 14 years old, he becomes an errand boy for George Rebow, a bookbinder on Blandford Street in London. 7-year apprenticeship. He binds books during the day and reads them at night. Every volume that passes through his hands becomes his textbook. Isaac Watts's The Improvement of the Mind. Jane Marset's Conversations on Chemistry. He builds a crude electrostatic machine in the back of the shop, joins the City Philosophical Society in 1810, attends lectures on science with borrowed money, 1 shilling per lecture. He takes notes in perfect handwriting, draws diagrams with perspective training from a French artist who lodges above the shop. A customer named William Dance gives Faraday tickets to 4 lectures by Humphrey Davy at the Royal Institution. Davy is the most famous chemist in Britain, discovered sodium and potassium using electricity, invented the miner's safety lamp. Faraday attends every lecture, takes 300 pages of notes, binds them in leather, sends the book to Davy with a letter asking for any position in science, however lowly. Davy's reply is kind. No positions available. Faraday returns to bookbinding for another year. Then Davy injures his eyes in a nitrogen trichloride explosion. Needs an assistant. One of the Royal Institution's lab assistants named John Payne gets sacked. Davy remembers the bound notebook. March 1st, 1813. Faraday is a appointed chemical assistant at the Royal Institution. 21 years old, salary of £1 per week. 2 rooms at the top of the building. Publishes in July 1820. The scientific community erupts with questions. If electricity makes magnetism, can magnetism make electricity? Can this effect create useful motion? André-Marie Ampère in Paris immediately begins experiments. Develops mathematical laws of electromagnetic force, shows that 2 current-carrying wires attract or repel depending on current direction, calls it electrodynamics, proposes that all magnetism comes from circulating electric currents inside matter, revolutionary concept, but purely theoretical, mathematical, no practical mechanism, sees what they miss. They're trying to make a wire rotate around its own axis. Faraday realizes you need the wire to orbit around a fixed magnet, or a magnet to orbit around a fixed wire. The force must have a center. September 4th, 1821. Faraday builds 2 devices producing what he calls electromagnetic rotation. One is now called the homopolar motor. A wire dips into a pool of mercury in a glass container. A bar magnet stands vertically in the mercury with its north pole up. Connect battery. Current flows down the wire into the mercury. The wire begins to rotate continuously around the magnet in circles, clockwise or counterclockwise depending on which battery terminal connects to the wire. Reverse the current direction. Rotation reverses. Continuous circular motion from electromagnetic force. The first electric motor. The second device does the inverse. A magnet suspended by a thread hangs with its lower end in mercury. A fixed wire stands in the mercury nearby. Pass current through the wire. The magnet rotates around the wire as its center. Same principle, different geometry. Both prove that electromagnetic force can create continuous mechanical work, not just momentary deflections. Sustained motion. He publishes in October 1821 in the Quarterly Journal of Science. Describes the apparatus, draws detailed diagrams, explains the circular nature of magnetic force around a current-carrying wire. But he does not credit Davy or Wollaston with the initial problem, does not mention their failed attempts, does not acknowledge their conversations with him. Controversy erupts immediately. Wollaston accuses Faraday of stealing the idea. Davy feels betrayed. His protege has published electromagnetic rotation without mentioning Davy's input. The Royal Society investigates. Faraday is cleared. His work is original. His mechanisms are different, but the damage is done. Davy feels hurt. Their relationship cools. Never breaks entirely, but never fully recovers. When Faraday is proposed for a Royal Society Fellowship in 1824, Davy initially opposes, eventually relents. Faraday is elected, becomes Fellow of the Royal Society at 32 years old. Davy later says his greatest discovery was Michael Faraday. Perhaps an attempt at reconciliation, perhaps genuine recognition. Both men move forward. The shadow remains. Discovers benzene in 1825 while analyzing the oily residue from illuminating gas. The chemical formula is 6 carbon atoms and 6 hydrogen atoms arranged in a ring. Benzene becomes the foundation of organic chemistry in the chemical industry. Becomes director of the laboratory in 1825 at 33 years old. His reputation as an experimental chemist is unmatched. He improves optical glasses, creates new alloys, studies diffusion of gases, teaches chemistry courses, delivers public lectures. The Royal Institution depends on his lecture income to survive. Friday evening discourses, Christmas lectures for children. He is a brilliant communicator, makes complex ideas accessible, demonstrates experiments with dramatic effect. But underneath the chemistry and the teaching, the question haunts him. If electricity creates magnetism and electromagnetic force creates motion, can magnetism create electricity? Can the process reverse? Paragraph 612. Placed a coil near a strong horseshoe magnet. Closed the circuit. Watched galvanometer for hours. Needle remains at 0. Paragraph 893. Moved a wire through a magnetic field. Expected current. None detected. He wraps coils near magnets. Nothing. He moves wires near steady magnetic fields. Nothing. Static magnetism refuses to generate current. The effect must exist. Symmetry demands it. If current makes magnetism, magnetism must make current. But how? Every attempt fails. He tries stronger magnets, more sensitive galvanometers, different wire configurations, different metals, copper, iron, silver, gold, all fail. The physics community moves on to other problems. The symmetry is broken. Electricity creates magnetism. Magnetism does not create electricity. That is the verdict by 1830. Faraday does not accept it. Keeps trying, keeps failing, keeps thinking. 5 coils total wound around different parts of the ring. One coil connects to a voltaic battery made of 10 pairs of plates. The other connects to a galvanometer placed 1 meter away from the ring, far enough that the battery's magnetic field cannot reach the galvanometer directly through air. This distance is crucial. Eliminates the possibility that current in the battery circuit directly affects the galvanometer. Any effect must travel through the iron ring via magnetic coupling. The iron ring is the key insight. Iron concentrates magnetic fields. When current flows through the first coil, the iron ring becomes magnetized, acts like a temporary magnet, channels the magnetic force through its structure. Faraday expects this magnetization to induce steady current in the second coil. Expects that as long as the battery remains connected, current should flow in both coils. He closes the battery circuit, watches the galvanometer needle intently. The needle jumps sharply to the side, then immediately returns to 0. Current is flowing steady through the first coil. The ring remains magnetized. Galvanometer needle stays at 0. No continuous current in the second coil. He watches for several seconds. Nothing. Opens the circuit. Disconnects the battery. The needle jumps again. Same magnitude, opposite direction. Returns to 0. Only change produces current. Only when the magnetic field is growing or collapsing does electricity appear in the second coil. The moment of switching, on or off, the transition, not the steady state. This is not what anyone predicted. Oersted showed steady current creates steady magnetism. Ampere's mathematics describes forces between steady currents. Everyone expects static magnetism to create static electricity. Faraday finds the opposite. Steady magnetism does nothing. Changing magnetism creates electricity. The rate of change matters. Not the field strength, the derivative, not the value. The galvanometer needle spins rapidly 4 or 5 full rotations before air resistance and Earth's magnetic field slow it to oscillation. Opens the circuit, needle spins the opposite way. The effect is violent, unmistakable. He replaces the iron ring with copper. The induced current becomes far weaker, almost identical to having no ring at all. Iron amplifies the effect by concentrating the magnetic field. This ring is the first electrical transformer. It survives. On display at the Royal Institutions Museum, one of the most important scientific objects in history. Published in March 1832, just months after Faraday's discovery, and from the detailed analysis in the 2015 commentary published in Philosophical Transactions A, examining Faraday's original laboratory notebooks held at the Royal Institution, which record his experiments paragraph by paragraph with precise dates and instrument readings that we can verify today. Now back to the information. September 1831, days after the ring experiment. Faraday realizes something profound. If changing current in one coil induces current in another, then moving a magnet should do the same. He takes a hollow coil of wire, connects both ends to a galvanometer, grabs a permanent bar magnet, thrusts it quickly into the coil. The needle deflects, pulls the magnet out. Needle deflects the opposite direction, pushes and pulls repeatedly. The needle vibrates in perfect phase with the magnet's motion. Electromagnetic induction, the phenomenon that will power every generator and transformer on Earth. Faraday does not stop. Continuous direct current flows from axis to rim. Rotate faster, more current. This is the principle behind every electrical generator ever built. Mechanical motion plus magnetism equals electricity. The inverse of the motor, he patents nothing, publishes everything. The world's first dynamo, September 1831, 1 month that changes human civilization. Something that will matter more than the induction itself. He watches iron filings scatter on a thin card placed over a magnet. Everyone has seen this demonstration. Place a card over a bar magnet, sprinkle iron filings on the card, tap it gently. The filings form curves, lines, chains stretching from North Pole to South Pole. Beautiful patterns, symmetric, predictable. Everyone sees the pattern. Faraday sees physical reality. He coins the term in his 1831 laboratory diary paragraph 50, magnetic curves. Later evolves to lines of magnetic force. By 1845, he begins using the phrase magnetic field more frequently in his papers and lectures. The region near the poles where these lines exist, where magnetic action occurs. He describes them precisely in his 1831 first series of experimental researches presented to the Royal Society. The exercise of magnetic force, which is exerted in the lines usually called magnetic curves, which equally exist as passing from or to magnetic poles or forming concentric circles round an electric current. These lines, he argues, are not mere visual patterns, not convenient fictions for drawing diagrams. They represent something real existing in space. Most scientists in 1831 treat these lines as mathematical conveniences, geometric constructions useful for calculation but having no physical existence, like latitude and longitude lines on a globe, helpful for navigation, not actually present on Earth's surface. The force, they believe, acts instantly between magnet and iron across empty space. Action at a distance. Newton's gravity model applied to magnetism. Two objects. Empty space between them, instant force, no medium, no propagation time, clean, simple, mathematically elegant. Faraday insists they are wrong. The lines are real, physical objects filling space, entities with their own properties. He argues this in his 1852 paper on the physical character of the lines of magnetic force, presented to the Royal Institution on June 11th. His most explicit theoretical statement. He lays out multiple arguments for why the lines must have physical existence. First argument, they are curved. Gravitational attraction is purely radial, straight lines joining masses. Newton's law shows force decreases as 1 over distance squared along radial lines. No evidence those lines are anything but geometric abstractions. But magnetic lines curve. They loop from North Pole around to South Pole. They form closed curves. They bend around obstacles. They circle electric currents in concentric rings. Curved paths require contiguous transmission through a medium. Action must travel point to point, particle to particle, cannot jump across gaps along a curved path. Therefore, the lines are not mathematical abstractions. They are physical realities existing in space, trajectories along which force propagates through an intervening medium. He writes, I cannot conceive curved lines of force without the conditions of a physical existence in that immediate space. Faraday has no mathematics beyond simple algebra, cannot use trigonometry. His ideas are qualitative, visual, physical. The scientific establishment dismisses them as the imaginings of an uneducated experimenter who does not understand proper theory. William Thomson, later Lord Kelvin, and James Clerk Maxwell respect Faraday's experimental genius, but consider his theoretical ideas crude, needing translation into real physics, real mathematics. Faraday does not care. He knows what he sees. In 1832, he begins calling all forms of electricity the same force: the spark from a static generator, the current from a voltaic battery, the pulse from electromagnetic induction, the shock from an electric eel, all identical, all different manifestations of the same power moving through contiguous particles, not a fluid flowing through wires, not an imponderable substance. A state of tension in matter, a forced electrical arrangement, he writes. Particles strain against each other. When the tension grows too great, they rearrange. Current flows. By 1836, he builds the first Faraday Cage, a room lined with conducting material. Step inside while someone generates massive sparks outside. You feel nothing. The charges redistribute on the cage's surface. The field inside becomes zero. The cage does not block electricity. It redirects the lines of force around the interior space. Proof that space and its lines are what matter, not the charges themselves. 1841. He begins to recover, returns to the laboratory, experiments on new glasses, searches for connections between light and magnetism. Takes a piece of optical glass with high dielectric constant, the heavy lead borosilicate glass he perfected in the 1820s, shines polarized light through it, places the glass between the poles of a powerful electromagnet with the light traveling parallel to the lines of magnetic force, uses a nickel prism to check if the plane of polarization rotates. It does. When the electromagnet is active, the plane rotates. Switch off the magnet. Rotation stops. The amount of rotation depends on the field strength and the distance traveled through the glass. September 13th, 1845. He writes in his notebook, "I have at last succeeded in illuminating a magnetic curve or line of force and in magnetizing a ray of light." The first evidence that Maxwell will use years later to argue that light is an electromagnetic wave. But Faraday sees something deeper. If magnetism can twist light and light is wave motion, then magnetism must involve wave motion. And if magnetism propagates as waves, it cannot be instantaneous action at a distance. It must take time to travel. It must move through a medium. The medium is the field. The lines of force that he insists are real. In 1846, he publishes Thoughts on Ray Vibrations in Philosophical Magazine, speculates that light might be vibrations in the lines of force themselves. No ether needed, just the field, just the lines stretching and oscillating. The paper is ignored. He lays out arguments for why the lines must be physically real. They are curved. Gravitational attraction is purely radial, along straight lines joining masses. No evidence those lines are physical, but magnetic lines curve. They loop from north to south pole. They circle electric currents. Curved paths require contiguous transmission through a medium, point to point, particle to particle. Therefore, the lines are not mathematical abstractions. They are physical realities existing in space. He defines precisely what he means by physical existence, a physical existence in that intermediate space through which the force is exerted. The total power contained in any cross-section of that line is exactly equal to the power in any other cross-section of the same line. The lines cannot be created or destroyed, only redirected, reshaped. They are conserved entities, like mass, like energy. This is field theory emerging from experimental intuition. Instant forces between particles. Clean equations. Faraday continues experimenting. 1845. He discovers diamagnetism. Most materials are weakly repelled by magnetic fields. He suspends a piece of bismuth between magnet poles. It orients perpendicular to the field, trying to move away. He tests dozens of substances, measures their responses. All matter interacts with magnetic fields. Even vacuum might have properties. Even empty space might be a substance if the lines of force fill it. He is a theorist of the highest order, one whose theory is expressed in physical intuition rather than symbols. Maxwell writes that Faraday's methods show him to have been in reality a mathematician of a very high order, one from whom the mathematicians of the future may derive valuable and fertile methods. Maxwell begins translating Faraday's lines into mathematical language, treating the field not as a calculation tool but as a physical entity with its own equations and dynamics. How changing magnetic fields create electric fields. The equations predict that electromagnetic disturbances propagate as waves. He calculates the speed. It matches the speed of light measured by Fizeau and Foucault. Light is an electromagnetic wave, a vibration in the field. Faraday was right. The lines are real. The field is a physical thing that can oscillate and carry energy at finite speed. But Maxwell still thinks the field is a property of the luminiferous ether, that invisible substance supposedly filling all space through which light propagates. Faraday, by the 1850s, has abandoned the ether. He writes in letters that the lines of force need no medium beyond themselves. They exist in vacuum. The field itself is the substance, not vibrations in something else, vibrations in the field. This distinction takes physicists 50 more years to accept. Not until Einstein's 1905 relativity paper will they abandon the ether entirely and accept that fields are fundamental realities, entities that can exist and propagate without any underlying substance. Refuses a knighthood, refuses the presidency of the Royal Society, tells the government he will not help design chemical weapons for the Crimean War. Ethical reasons. 1858. Queen Victoria grants him a Grace and Favor house at Hampton Court. He retires there, continues small experiments and correspondence, reads scientific papers, watches the younger generation slowly accept field theory. Faraday dies at Hampton Court, 75 years old. His funeral is simple, no state honors, buried at Highgate Cemetery. Few obituaries mention the lines of force or field theory. They focus on his discoveries: electromagnetic induction, the laws of electrolysis, diamagnetism, the benzene molecule, the Faraday effect, practical achievements, tools for industry. The deeper conceptual revolution he started goes mostly unrecognized. 1873. Maxwell publishes A Treatise on Electricity and Magnetism, the full mathematical formulation of electromagnetic field theory, 4 equations that unify electricity, magnetism, and light. The equations use the mathematics of vector fields, divergence, curl, gradient, concepts that describe how quantities spread through space and how they circulate and how they change point to point. The language of fields. Faraday's lines translated into calculus. Maxwell dedicates the work to Faraday's memory, calls him the father of the enlarged science of electromagnetism. But the physics community still does not fully grasp what Faraday understood. They treat the field equations as elegant ways to calculate forces, not as descriptions of a new kind of physical reality. Heinrich Hertz in Germany generates electromagnetic waves in his laboratory, uses a spark gap oscillator, detects the waves with a loop antenna across the room, proves Maxwell's equations are correct, proves that electromagnetic disturbances propagate at the speed of light, proves they reflect and refract and interfere like any waves. Radio waves, the first technology directly based on field theory. Still, physicists think the waves travel through ether. If you move a conductor near a stationary magnet, you explain it another way. But the result, the current induced, depends only on their relative motion, not on which object is considered moving. Classical theory gives different explanations for the same phenomenon depending on your reference frame. Einstein resolves this by eliminating absolute space. Motion is relative. Electric and magnetic fields are also relative. They are 2 aspects of a single electromagnetic field that appears different to observers in different frames. The field is what is real, not the ether, not absolute space, just the field. This is the culmination of Faraday's insight. Space is not empty. It contains fields. Fields are physical. They carry energy and momentum. They propagate at finite speed. They're fundamental. Gravity itself becomes a field, a curvature in space-time. The gravitational field has its own equations, its own dynamics, its own physical reality. No action at a distance. No instant forces across the void. Everything propagates through fields at the speed of light or below. Contiguous causation, point to point. Exactly as Faraday intuited in the 1830s when he argued that forces must travel along curved lines through a medium. The medium is the field. The field is space-time itself. Quantum field theory emerges. Every particle is a vibration in its corresponding field. Electrons are excitations in the electron field. Quarks in quark fields. The Higgs boson is a ripple in the Higgs field. Fields fill all of space. They overlap. They interact. Reality is fields all the way down. Faraday was more right than he knew. Not just magnetic fields and electric fields. Everything is field. The experimental confirmation took another 50 years, but the conceptual core came from a man with no formal mathematics, a bookbinder who read every book he bound, who looked at iron filings on a card and saw not a pattern but a network of real physical lines stretching through space, who insisted that empty space was full, that forces did not act at a distance, but propagated through contiguous action along field lines, that the lines were not abstractions, but substances, who faced ridicule from mathematical physicists who said he did not understand theory, who kept experimenting and kept insisting and kept seeing what others could not see. You can see the actual apparatus that Faraday used on August 29, 1831, the laboratory notebooks at the Royal Institution Archive, 3,000 numbered paragraphs of experimental research in electricity alone, every result dated, every observation recorded, drawings of apparatus, measurements of deflections, the moment-by-moment documentation of how field theory was born from experimental facts. His papers in the Philosophical Transactions of the Royal Society, 116 papers on electricity and magnetism from 1831 to 1855. Read them. The language is clear, direct, no jargon, no mathematical intimidation, just careful description of what happens when you move magnets near wires and spin disks between poles and pass light through glass in a magnetic field. Named 1881, the Faraday constant in electrochemistry, 96,485 coulombs per mole. The charge carried by 1 mole of electrons, fundamental to every battery and fuel cell. The Faraday Effect, used in optical isolators, devices that allow light to pass one direction but not the reverse, essential in fiber optic communications and laser systems. The Faraday Cage protects sensitive electronics from electromagnetic interference. Every server room, every MRI scanner, every aircraft uses the principle Faraday demonstrated in 1836. The field redistributes on the conducting surface. The interior remains field-free. They all rotate wire coils in magnetic fields to generate electricity. Every electric motor reverses the process, pass current through coils in a magnetic field, force them to rotate. Every transformer relies on his iron ring experiment. Changing current in one coil induces current in another through magnetic coupling. Step voltage up for long-distance transmission. Step it down for household use. The entire electrical grid is Faraday's discovery multiplied 1 billion times. Capable of transmitting vibrations, capable of being warped and curved. Field theory did not emerge from pure mathematics. It emerged from a man looking at iron filings and refusing to accept that the pattern was not real, insisting the lines must exist, must be physical, must fill the apparently empty air between magnet and iron. When asked why, he said Maxwell built on Faraday. I built on Maxwell. The chain goes back to the bookbinder who saw what no one else could see, who looked at a compass needle twitching near a wire and understood that space itself was doing something. Not the wire acting on the needle across the gap. The space between them was under tension, was transmitting force, was real. The National Research Program for Battery Science and Energy Storage, named for the man who discovered the laws of electrolysis, who understood that chemical reactions and electrical currents are two manifestations of the same electromagnetic field, energy rearranging atoms. His experimental methods still guide electrochemistry research. His clarity of thought still sets the standard. Faraday never developed that. The genius was seeing the physical reality beneath the mathematics. Maxwell gave us equations. Einstein gave us relativity. Quantum mechanics gave us field quantization. But Faraday gave us the idea, the core concept, that fields are real, that space is not empty, that forces propagate through media filling the void. Everything else followed from that. Without Faraday's insistence that his lines of force were physically real, Maxwell might have treated his equations as mere calculation tools. Without Faraday's rejection of action at a distance, Einstein might not have looked for finite propagation speeds. Without Faraday's experimental proof that changing fields create other fields, quantum field theory might have taken decades longer to emerge. He thought the lines of force were the fundamental substance. We now know fields are more abstract than that. They are mathematical objects, tensors, operators on Hilbert space. The lines are just a visualization, useful but not fundamental. He abandoned the ether. Correct. But he thought the field could exist in pure vacuum with no underlying structure. Quantum mechanics reveals vacuum is seething with virtual particles. 0-point energy. Vacuum is not nothing. It has structure, properties. Faraday intuited this, did not get the details right, but the intuition that vacuum is something was correct. A coil generates current. Light rotates its polarization. He asked what is happening in the space where no objects exist, what is carrying the influence from here to there, and he concluded the only answer was that space itself must have properties, must be capable of states of tension and relaxation, must be capable of transmitting vibrations, must be filled with something real. He called it lines of force. We call it the electromagnetic field. Same concept, different language. It required abandoning common sense. It required trusting experimental results over philosophical prejudice. It required the courage to say, my mathematical colleagues are wrong, even though they have all the credentials and I have none. He wants to test whether magnetic fields affect the spectral lines of light. Takes a powerful electromagnet, places a gas discharge tube between the poles, observes the spectrum with a primitive spectroscope, looks for shifts or splitting in the spectral lines when the magnet is turned on, sees nothing conclusive. The equipment is not sensitive enough. He records the attempt, notes that better apparatus is needed, moves on. 35 years later, Peter Zeeman performs the same experiment with improved equipment, finds the spectral lines do split in a magnetic field, receives the 1902 Nobel Prize in Physics for discovering the Zeeman effect. His Nobel lecture credits Faraday. Says Faraday tried this experiment in 1862 and was limited only by technology. The idea was right. The intuition was right. The equipment was not yet good enough. That was Faraday, right about the physics, ahead of the technology, ahead of the mathematics, ahead of his time. But that is not the deeper discovery. The deeper discovery is that space is not empty, that magnetic force is not instant action between distant objects, that the region between magnet and iron is filled with lines of tension that are as real as the iron itself. He spent 40 years arguing this point, was rejected by his peers, died before seeing full acceptance. His induction ring still sits in a museum case in London, 6 inches of soft iron. 5 coils of copper, the transformer that transformed physics, the apparatus that proved fields are real.